We're told that the diameter of the pin at A is again 6 millimeters. At D, it's going to be 10 millimeters. And the mass of the bucket it's supporting is 150 kilograms. We will find the shear stress in the pin at A and the shear stress in the pin at D. Right, so what are all the things we're going to need to find in order to get the shear stresses in the pin at A and the pin at D? Yeah.
Tension on the cable. So that you can get the pin at C.
Right. So we need to, I guess, more conceptually, why we need any of that? So, kind of starting at the end, working our way. If we want the stresses at the pin at A, the pin at D, what do we need to calculate that? Yeah.
The external reactions.
Right. We're going to need the external reactions so that we could find.
Internal.
Right. These are based on internal shear forces, that V. We're going to need the internal shear force at A and the internal shear force at D to calculate the stresses and the pin at A and the pin at D. To get those internal forces, that's where we're going to need to find these external forces. They're acting on those pins. So at A, we have this pin connection, which we were modeling last semester with that X component, that Y component. And at D, what force is going to be pulling on the pin at D?
Force along BD.
Right, so BD, and what type of member is BD? Right. BD is a two-force member, which we can use to simplify our analysis a little bit. So this is a frames and machines type question. We need to do those external parts first to find what these forces are that act on the pins. Once we know the forces that act on the pins, then we can look at the stresses, the average shear stresses in those pins. So ultimately what we need to find is what is AX, AY, because those are the forces that the pin puts on the member. Therefore, the member puts the equal and opposite forces on the pin. And then at D, we need to know what's that force, because if we know the force that the pin has on D, then we know the force that the member D, BD, has on our pin. So we need to start with the frames and machines question first. In this case, I'm actually doing this one a little bit differently than I would have in EMCH 211. I am actually drawing the external free body diagram here so I can avoid the complication at C, as we'll see in the second free body diagram. So I'm going to do the entire external free body diagram here. At A, I have that pin connection with an AY and an AX. At E, I have the weight of the bucket, the 150 kilogram bucket. So there's going to be a force of 1,470 newtons. And at C, this is where I have the tension in the wire going from C to F. And we're told that makes a 30-degree angle with the vertical. This is the external picture. I can't see the force at B and D because I can draw it here if I want. But those to this picture are internal, and I'm not seeing what happens. In the second picture, when I separate it out, then I'm going to be interested in what's happening at C and at D. By solving this, we're going to be able to find AX and AY. TCF we'll find along the way. We're not going to be that concerned with it for this particular problem. But we need AX and AY since those are the forces the pin exerts on the member ABC. And then the equal and opposite will be what ABC does to our pin. In this picture, though, we don't have the force that the two-force member BD is applying at D. So we're going to need a second free body diagram that will include that force. Now we have our choice of what we want to do. we could draw a member ABC, and that would include the force from that two-force member. I chose to draw CDE, which will also include the force from BD when I remove that from my picture. Either one, I should get the same results. At point D, I have the force from member BD. Since CD is 0.6 and CB is 0.6, I know that this makes a 45-degree angle with the horizontal. I have the applied load at the end from the bucket of 1470 newtons. Point C gets a little bit trickier than some of the things we saw last semester. We have a pin connection between CDE and ABC, but we also have an applied load acting there. So we can't just draw equal and opposite forces of CX, CY in this and the other picture. We have to do like what we did last semester, where we had to draw what was the pin at C doing to CDE, ABC, and to the rope attached at C. We actually don't care what that value is for this problem, so I can just model it as a CY1 and a CX1. Again, this goes back to what we saw last semester. We don't need to actually find these, but if we were interested, we could go through that whole process, draw the pin at C, and find out what's actually happening to that. In this, though, we just care about A and D. I won't go through all the details from the 211 part of this, but from picture 1, I can sum forces X, sum forces Y. I can take the sum of moments around A, and I can get the 3 unknowns that I have there. Most importantly, AX is 980 newtons, AY is 3170 newtons to 3 digits of precision. In picture 2, again, I have only 3 unknowns, so sum of forces. Really, all I need is sum of moments at C. I can find the force in BD. Negative 4160 newtons. So that member turns out to be in compression. I'll mark it here, but for the purposes of this problem, we don't care that much. We have our external forces or our pin forces, but we don't have any internal forces, at least in terms of being able to analyze stresses yet. So we're going to need additional pictures that show what those stresses are. This is going to be important looking at the cross-section or the other view at A and at D. So we see how A is attached here is that the pin goes through that member, and then there's going to be a bracket at both sides. So this is going to be a pin in double shear. And at D, we have the same process. That member BD actually has a fork and is attached to both sides of the member, not just one side of the member. And again, that's going to have an impact to what's that internal shear force and therefore the internal shear stress going to be at A and at D. If I draw an internal picture of the pin at D, what I want to do is I want to know what is the shear force in that pin. So I'm just drawing the pin at D. For shear stresses, for the most part, the directions don't really matter. I'm just going to represent an overhead view here. On the cut surfaces, I'm going to have the shear force at D, which I'll call V sub D. Again, because it's in double shear, the shear force is on both sides of that cut. Just kind of blowing it up here. What I'm doing to make this cut is I'm making a cut through this left part of the pin and this right part of the pin. So both sides of those, both internal forces are therefore exposed. And then what is the force that's going to be acting on the pin? The external force acting on the pin. Right, the force in BD, because that's going to be pulling on the pin, or the pin was pulling on it, putting it into actually compression. So an equal and opposite force is acting here with a value of 4160 newtons. Again, for shear force, the directionality for the materials we're talking about don't really matter, but we do want this internal picture to illustrate that it's in double shear. So when I go to picture D, I know that the force V sub D is going to be half of the 4160. All right, so we'll come back to that. We know what the internal shear force is at D. We also need to know what the internal shear force at A is. And if we look down there, A is also in double shear. For the pin at A, what is the force acting on the pin at A? When we did this analysis, for mathematical simplicity, we said that a component of the force was in the x direction, a component of the force was in the y direction. In reality, it is only one force off at some angle there, but it's harder if we want to try to find the magnitude of the force and the angle it makes. It's harder mathematically to do that, but we can, like we saw last semester, convert from the Cartesian to the polar coordinates if we're interested in. We can assume that the pin, no matter what angle the force is acting at, the pin is going to behave the same. Again, for different materials, that might not be true. But really what we care about is what's the magnitude of the reaction from that pin. So that's where this 3320 comes from. We need to take the square root of the sum of the squares of the components of the force at A. So if we take the square root of 980 squared plus 3170 squared, we should get a number 3320 newtons as the total force that the member ABC is exerting on the pin. So we do want to go from the components into the actual magnitude for these calculations. Again, these are in double shear, so that's why we have two sides of the pin. If these were in single shear, like there was only one bracket here, now you imagine we cut through this pin. The other side, there's nothing resisting that, so we would only have one internal shear force there. So if these were in single shear, the internal loads would be twice this, or equal to what that applied force is. So we would find that the internal, the shear stress would also be twice as much. We have the internal forces. Now we can finally answer the question, what is the shear stress at A, the pin at A, and the shear stress in the pin at D, or at least the average shear stress. At A, it's going to be V over the cross-sectional area at A. It's actually the same cross-sectional area we had before, the diameter of 6 millimeters. So that's pi over 6 times 10 to the negative third squared over 4. The shear stress at A is then 59 megapascals. Right? Or 59 times 10 to the 6th pascals. And at D, this is the easy calculation. The internal shear force is 2,080 newtons. But also the cross-sectional area at D, not only is the shear force different at D, the cross-sectional area at D is also different because the diameter of the pin is different at D. So the area will be pi times 10 to the negative third squared over 4. Shear stress at D, we get 26.5 megapascals.